Module 8, Lecture A, Curved Relationships. By the end of this lecture, you will be able to recognize visual patterns in data that suggest nonlinear relationships, describe how adding transformed features can create curved prediction shapes, and explain the trade-off between flexibility and overfitting in nonlinear models. Seeing curved patterns, recognizing curved trends. When you look at a scatter plot, check whether the points follow a straight path or a curved one. A curved trend appears when the direction or steepness of the relationship changes as you move along the horizontal axis. For example, study hours and exam scores may rise quickly at first and then level off, showing diminishing returns. This kind of bending pattern means a straight-line model is not appropriate for describing the data. Curved trends in data occur when the rate of change is not constant, so a straight line cannot describe the pattern. You might see a gentle arch, a curve that starts flat and then rises sharply, or a quick rise that levels off into a plateau. In each case, the best mental line through the points would need to bend to follow how the data changes. Recognizing these curved shapes helps you quickly identify when relationships are not linear. To detect curved trends in data, look at how your eye naturally connects the points and ask whether a straight line fits well. If a straight line leaves many points above it in one region and below it in another, that suggests the relationship is curved. For instance, age and income may rise together in mid-career, then level off or fall near retirement, which a straight line would miss. This kind of consistent bending away from a straight line, often seen in engineering and environmental data, shows that a curved model is more appropriate. Limits of straight lines. Using a straight line to summarize data assumes that the outcome changes at a constant rate for each unit change in the predictor. In other words, the line increases or decreases steadily across the entire range of the data. This is a simple but restrictive assumption. When you imagine laying a straight edge through a scatter of points, you are asking whether one overall trend can describe the main pattern. If the points consistently fall above the line in some regions and below it in others, it shows that a single straight line may not capture changes in how fast or in what direction the relationship shifts. Many real-world processes do not follow a straight line pattern. For example, learning may improve quickly at first, and then slow down, and medication effects may rise with dosage and then level off or even decrease. A straight line cannot accurately capture these curved patterns and will either underestimate or overestimate important changes. This shows why we need more flexible models that can better reflect how the data actually behave. When we fit a straight line to data, its limitations often show up in the residuals, which are the differences between the actual data points and the line. If these residuals form a pattern, such as being mostly above the line in one region, below in the middle, and above again later, this suggests the true relationship is curved rather than linear. For example, electricity demand versus temperature may be low at mild temperatures, but rise in both hot and cold conditions, creating a U-shaped pattern. In such cases, a straight line cannot capture the real behavior of the data, and more flexible models are needed. Python code. Limits of straight lines. This script visually demonstrates the limitations of using a straight line to represent data. It compares a straight line to a curved pattern and highlights where they do not match. As you watch, focus on noticing the gaps and mismatches between the line and the actual data. This helps you see when a straight line is not an appropriate fit. The comments in the code explain that the plotting libraries are already available when using Colab, which is a cloud-based Python environment. If you run the same code outside Colab, you may need to install these libraries yourself using the Python package installer. An example command in the comments shows how to install Matplotlib, Seaborn, and NumPy. Doing this ensures that all required tools for plotting and numerical work are available, so the script runs correctly. We begin by importing two key tools: a numerical computing library for handling data and calculations, and a plotting library for creating visualizations. These imports provide the basic functionality needed to work with numerical data and to display results as graphs. They form the foundation for the data processing and plotting tasks used throughout the script. We set the random seed in the NumPy random number generator to the value 42 so that any random numbers produced will be the same every time the code runs. This makes the results reproducible, which is important for debugging and checking that the code behaves as expected. By fixing the seed, we can reliably repeat experiments and verify that changes in output are due to code changes, not random variation. We begin by creating predictor values that are evenly spaced along one dimension using a numerical tool that generates a sequence of numbers. In this case, we choose values ranging from -3 to +3 and ask for 40 points in total. This gives us a smooth, consistent set of x values. We can then use these values to study relationships in our data, such as when plotting curves or fitting models. We define a curved or parabolic relationship by taking each x value, squaring it, and multiplying by 0.6. Then we add 1 to shift the entire curve upward so it does not start at 0. This creates a simple quadratic pattern that we can later compare to how well a straight line fits the same data. We add randomness to our data by generating noise values drawn from a normal distribution with mean 0 and standard deviation 0.8. The size of this noise array matches the number of predictor values so that each input has its own noise component. We then add this noise to the true curve to mimic real-world variability, causing the observed data points to scatter around the underlying curve. In this step, we combine the ideal curve with the noise values to generate the observed outcomes. By adding randomness to the true curve, we simulate how real-world data behaves. This process introduces effects like measurement error and natural variability. The result is a more realistic dataset that better reflects what we would see in actual observations. We use a polynomial fitting function from NumPy to fit a straight line to our data. It takes the predictor values, the observed outcomes, and the desired polynomial degree as inputs. By choosing degree 1, we fit a linear model and obtain the slope and intercept of the best fitting line, stored together as the line coefficients. This fitted line is then used to see how well a simple linear model can approximate the underlying curved relationship in the data. We use the NumPy polyval function to evaluate the fitted straight line at all predictor values. It takes the line's coefficients and the input x values, then computes the corresponding y values for each x. In other words, it applies the linear equation defined by the coefficients to every x, producing the y values that describe the straight line fit. We calculate residuals by subtracting the model's predicted values from the observed values. These residuals show how far each actual data point is from the value given by our fitted straight line. By examining them, we can judge how well the line fits the data overall. Patterns or large discrepancies in the residuals indicate that the line may not be capturing the underlying relationship accurately. The code reports a summary of the fitted straight line by printing its slope and intercept. These values come from the line fitting function in the numerical library, which stores the line's coefficients. Seeing the slope and intercept together makes it easy to understand the main characteristics of the line that best fits the data. This line computes the average size of the residuals, which are the differences between the observed data points and the values predicted by the fitted straight line. It does this by taking the absolute value of each residual and then using a numerical library to find their mean. The result describes the typical amount by which the observed points deviate from the line, giving a measure of how well the line fits the data. We begin by creating a new plotting window using the figure function in Matplotlib and setting its size to 6 by 4 inches. Choosing this size helps keep the plot clear and easy to read. It provides enough space so that all elements of the visualization can be shown without looking crowded. We use a scatterplot to show the observed data points as blue dots, with predictor values on the horizontal axis and observed outcomes on the vertical axis. These outcomes reflect the true underlying curve plus some random noise. By looking at this plot, we can see how the observed data deviates from the true pattern and get a visual sense of the relationship between the predictor and the outcome. We use Matplotlib to draw the true curved relationship in our data by calling the plotting function with the x values and the corresponding true curve values. We color this line green so it stands out from other elements in the figure. We also give it the label true curved pattern so it appears clearly identified in the legend. This makes it easy for viewers to recognize that the green line represents the actual curved relationship we are comparing to the straight line fit. We use Matplotlib to draw the fitted straight line on the graph so we can see the linear approximation of the data. The line is shown in red and styled as a dashed line to make it stand out from other elements. We also label it as the straight line fit so viewers can easily recognize which line represents the linear model of the data. We label the horizontal axis to show that it represents the predictor values, often called x. This label tells viewers what the numbers along that axis stand for. By making the meaning of the horizontal axis clear, we give important context that helps people correctly interpret the plot. The code sets the label of the vertical axis to outcome value y, indicating that this axis shows the outcome measurements in the plot. This label tells viewers what the y-axis represents and clarifies the meaning of the data values. Adding such a label is important for making the visualization informative and easy to interpret. We add a title to the plot to emphasize that straight-line models have limitations when the data follow a curved pattern. The title quickly signals that the main purpose of the visualization is to compare a linear fit with a curved relationship. By doing this, viewers can immediately understand that a simple straight line cannot accurately capture the underlying curved trend in the data. The code uses the legend feature from the plotting library to add a legend to the graph. This legend labels the different elements in the plot, such as the observed data points, the true curved pattern, and the fitted straight line. Including the legend makes the plot clearer and helps viewers easily identify each component that has been drawn. We then use the show function from the plotting library to display the graph. This step lets us see the fitted straight line together with the curved data. By looking at the plot, we can visually judge how well the line matches the data and notice any clear mismatches between the model and the observed points. This script shows why a straight line is a poor model for a truly curved relationship. It creates predictor values, generates a curved pattern by squaring them, and then adds random noise to mimic real data. A linear regression line is fit to these noisy points, and the script reports the slope, intercept, and average residual size, which measures how far the predictions are from the observed values. The resulting plot contrasts the noisy data, the true curve, and the fitted straight line, making it clear that the line struggles to follow the curved pattern accurately. Spotting nonlinear shapes. To decide if a relationship in a scatterplot is curved, look at the overall pattern of the points rather than individual dots. A curved or nonlinear relationship appears as a smooth bend instead of a straight line. For example, study time and exam scores might rise quickly at first and then level off, forming a flattening curve. Car speed and fuel efficiency might form a hill shape, with higher efficiency at moderate speeds and lower efficiency at very low or very high speeds. In both cases, the key idea is that the data follow a smooth curve that clearly departs from a straight trend. Nonlinear patterns in data occur when the relationship between variables bends or changes direction instead of following a straight line. Common shapes include U-shaped curves, where values are high at both low and high levels of a predictor, but lower in the middle, and inverted U-shaped curves, where values rise and then fall. Another example is an S-shaped pattern, which starts off flat, becomes steep, and then flattens again, as seen in the adoption of new technologies. Recognizing these curved patterns is important because a straight line cannot accurately describe how the data behave across the range of values. To spot nonlinear patterns, imagine fitting a straight line through your data and look for where it consistently misses. If points tend to fall above the line in one region and below it in another, this alternating pattern suggests a curved relationship. For instance, temperature and electricity demand, or medication dose and symptom relief, may follow curves where a straight line fits only part of the range. Noticing these systematic deviations helps you decide when a curved model is more appropriate than a straight line. Curved predictions with features. Squared features intuition. A simple straight-line model assumes that each increase in a predictor changes the outcome by a constant amount, which only works well when the data follow a linear trend. When the true relationship curves, such as being weak at low values, stronger in the middle, and weaker again at high values, this linear assumption fails. By adding the squared version of the predictor to the model, larger values are emphasized, and the model can trace a curved pattern. Including both the original and squared predictor keeps the model linear in how it combines features, while allowing the predicted relationship to bend as the predictor changes. A squared feature tells the model to treat large predictor values differently from small ones by emphasizing bigger numbers. This helps the model learn patterns where the effect of a predictor speeds up, slows down, or reverses as it grows. For example, with study time and exam performance, early hours may improve scores, but too many hours can cause fatigue and reduce benefits. A model using only raw study hours might fit a straight line and miss this change in pace, while adding squared study hours lets it capture a curved relationship that can rise, flatten, or dip. Squared features help models capture situations where outcomes are best at a moderate level and worse when values are too low or too high. For instance, with exercise, very little activity is unhealthy, a moderate amount improves health, and too much can cause injury. By including both a feature, such as exercise time, and its square, the model can represent a curved relationship instead of a straight line. This same idea appears in economics with profit and price, in agriculture with fertilizer and crop yield, and in marketing with advertising and customer response. Feature interactions explained. Feature interactions occur when the effect of one predictor on the outcome changes depending on the value of another predictor. In a simple linear model, each feature influences the prediction independently, like separate controls. By adding an interaction term, often formed by multiplying two features, the model can adjust how one variable's impact varies with another. This lets the model create curved or tilted prediction surfaces instead of only additive, flat ones, and helps it handle specific combinations of conditions more accurately. When modeling how effective a medication is, it is not enough to look at dosage and age separately, because the effective dosage can change with age. A higher dose might help middle-aged adults more, but be less effective or even harmful for younger or older patients. By including an interaction between dosage and age in a linear model, we allow the impact of dosage to vary across ages. This creates a prediction surface that can twist and bend to reflect these nuanced relationships, even though the underlying model is still linear in its parameters. Feature interactions matter when the combined effect of conditions is more important than each factor alone. In marketing, for example, a discount may work differently depending on the time of day or a customer's purchase history. So interactions between discount levels and customer segments reveal how groups respond to promotions. In environmental science, the benefit of fertilizer on crop yield can depend on rainfall, where extra fertilizer helps only when there's enough water. By modeling these interactions, you capture real-world complexity and better understand how features work together to influence predictions. Python code. Feature interactions explained. This script visually demonstrates how features can interact in a model. It compares predictions from a simple additive model with those from a model that includes feature interactions. By focusing on the resulting prediction surfaces, it shows that interactions create curved, more complex shapes, while additive effects tend to produce simpler, flatter patterns. We begin by importing two key libraries for our work. NumPy is used to handle numerical operations efficiently, especially when working with arrays and mathematical calculations. We also import the pyplot module from Matplotlib to create plots and visualize data. Together, these tools let us perform complex numerical tasks and then display the results graphically, which helps us interpret and analyze the data more easily. We begin by setting the random seed in the numerical library to 0, so that any random numbers generated later are always the same each time the program runs. This makes the code deterministic and ensures that results can be reproduced. Reproducibility is important because it allows us to debug more easily and verify that the code behaves consistently across different runs. We begin by defining a range of values for the dosage feature using a function that creates 30 evenly spaced points between 0 and 10. These points represent different possible dosage levels in our model. By using this range, we can study how changing the dosage interacts with other features in the dataset. This helps us understand how varying dosage levels might influence the model's behavior and outcomes. We create a set of age values from 20 to 80 years old, using a numerical tool that generates 30 evenly spaced points in this range. This gives us a smooth spectrum from younger to older patients. We then use these age values to study how age interacts with other features in our model. We use a function from the numerical library to build a two-dimensional grid from the dosage and age values. This grid contains every possible combination of dosage and age, which lets us compute prediction surfaces across these pairs. The two resulting grids represent the dosage and age dimensions and form the basis for visualizing how these two features interact in our models. We use a simple additive model that treats dosage and age as independent effects. The model computes the overall effect by taking 0.3 times the dosage grid and adding 0.02 times the age grid. In other words, it assumes that dosage and age each contribute separately, and their contributions just add together without interacting or influencing each other. This line defines an interaction model that combines the effects of dosage and age. It includes a linear contribution from dosage and a linear contribution from age. On top of these, it adds an interaction term formed by multiplying dosage and age, scaled by a small factor. This interaction term captures how the effect of dosage changes with age, producing a more complex, curved prediction surface than a model that simply adds the two effects. The code verifies that the additive and interaction effect arrays have the same shape, so they line up correctly in later operations. This prevents unintended broadcasting, where mismatched dimensions could cause incorrect results or errors. By asserting that the shapes match, the code ensures the arrays are compatible for any further calculations or visualizations. We create a figure with two side-by-side subplots so we can visually compare two different models on the same canvas. The figure is sized to give enough room for both plots to be seen clearly. This layout is important because it lets us directly contrast the additive model with the interaction model and clearly see how their prediction surfaces differ. We start by plotting the additive model on the first subplot using a filled contour plot. Dosage and age form the horizontal axes, and the additive effect provides the vertical values that define the surface. We choose a set number of contour levels to control how detailed the plot appears, and apply a blue color map to distinguish it from other plots. This creates a clear visual of the additive model as a simple, straight prediction surface. The first subplot is titled to show that it displays the additive model surface, so listeners know what kind of model is being shown. The x-axis is labeled as dosage level, to indicate it represents different amounts of dosage in the model. The y-axis is labeled as age in years, to show it corresponds to the ages of individuals in the dataset. These clear labels make it easier to interpret the plot and understand the context of the data. We plot the interaction model to reveal how the prediction surface bends when dosage and age interact. In the second subplot, we use filled contours based on this interaction effect, with dosage and age forming the two axes. We choose several contour levels to show enough detail and apply a red color map to distinguish it from the additive model. This visual contrast makes it easier to see the curvature introduced by the interaction terms. In the second subplot, we title the graph Interaction Model Surface to show that it displays the interaction model. We label the x-axis as dosage level to indicate it shows different levels of dosage. We label the y-axis as age in years to show it represents patient age. Together, these labels clarify the dimensions and context of the curved prediction surface in the interaction model. The code first calls a function in Matplotlib that automatically adjusts the spacing between subplots, so labels and titles do not overlap and the layout looks clean. This makes the overall visualization clearer and more professional. It then calls another function in Matplotlib to display the final figure on the screen. As a result, you can visually compare the additive and interaction models side by side. This script compares additive and interaction-based prediction models using dosage and age as features. It produces two plots, one for an additive model with a flat, straight prediction surface, where the effects of dosage and age are simply added together, and one for an interaction model with a curved surface. In the interaction model, the curvature comes from a term that multiplies dosage and age, creating a more complex relationship between the features. The visual contrast makes it clear that adding interaction terms can dramatically change the shape of the prediction surface. How features bend predictions. You can think of a model as a flexible surface shaped by how we transform its features. A simple linear model with one feature produces predictions that change at a constant rate, forming a straight line. When we add transformations such as squared terms, interactions, or logarithms, we give the model new ways to bend and curve. Squared terms create U-shaped effects, logarithms rise and then level off, and interactions let the surface twist depending on combinations of features. The final prediction is a combination of all these influences, creating a more complex shape that can better match the data. In a simple linear model, plant growth is predicted as a flat surface that increases steadily with more sunlight or water. When we transform features, such as squaring sunlight, the prediction surface bends, so it can capture growth that first rises and then falls, when there is too much light. Adding interaction terms between sunlight and water further shapes this surface, showing that the benefit of extra water depends on the level of sunlight. Together, these transformations create a surface with peaks and valleys that better reflects the complex way plants actually respond to sunlight and water than a basic flat model can. In many fields, models use transformed features, so their predictions can match complex real-world patterns instead of simple straight lines. In finance, for example, using the square of the debt-to-income ratio helps capture how risk grows slowly at first and then rises sharply as debt becomes high, depending on employment stability. In healthcare, using age squared or combining age with comorbidity scores allows models to reflect how surgical risk stays low in early adulthood but increases rapidly with age and additional health problems. These transformations act like levers that shape the prediction curve to follow the natural behavior seen in the data. Python code: how features bend predictions. This script demonstrates how using different features can change a model's predictions. It compares predictions based on a simple linear feature with those based on a curved feature. The focus is on how adding a squared feature can bend what would otherwise be a straight prediction line. This helps illustrate how feature choice shapes the form of the prediction. We begin by importing a numerical computing library that lets us work efficiently with arrays and perform mathematical operations. We also import a plotting library that allows us to create graphs and visualizations. Together, these tools let us analyze data and visually explore how different features influence our predictions. We begin by setting a fixed random seed in the numerical library, using 0 as the value. This makes the sequence of random numbers the same every time the code runs, which ensures that our results are reproducible. It is especially important when we add noise to data, because it lets us consistently see the same effects and patterns in our analysis each time we repeat the experiment. We begin by creating a sequence of feature values that represent different levels of sunlight. Using a numerical tool that generates evenly spaced numbers, we produce 30 values ranging from 0 to 10. These values act as our independent variable and simulate varying sunlight conditions. They will be used as the basis for all further analysis in this example. We model the relationship between sunlight and plant growth with a mathematical formula that equals 4 times the sunlight level minus 0.4 times the sunlight level squared. This creates a curved pattern where growth increases as sunlight increases at first. However, because of the negative squared term, too much sunlight eventually causes growth to decrease. This captures the idea that there is an optimal range of sunlight for plant growth. To mimic natural variation in plant growth, we add random noise to the data. We generate this noise using a normal distribution with a mean of 0 and a standard deviation of 1, so the random values stay relatively small. The noise array is created to match the size of the sunlight data, giving each sunlight value its own noise value. Later, this noise is added to the true growth values to simulate observed growth that includes natural variability. In this step, we create observed growth values by adding random noise to the true growth values. This mimics real-world measurements, which almost always include some randomness or error. By combining the theoretical growth model with this noise, we generate a more realistic dataset. The result better reflects the natural variation we would expect to see in actual observations. We build a simple linear model to predict plant growth from sunlight levels, assuming growth increases at a constant rate as sunlight increases. The model starts with a base growth value of 1, and then adds 1 times the amount of sunlight. This creates a straight-line relationship between sunlight and growth. Later, we will compare this basic linear model to a more complex curved model. We build the curved prediction by starting with a constant value of 1, then adding a linear term that is the sunlight value multiplied by 1, which represents a direct increase in growth with more sunlight. To create curvature, we subtract a small amount based on sunlight squared, scaled by 0.1. This squared term makes the prediction bend, capturing the idea that growth does not keep increasing at the same rate, but shows diminishing returns as sunlight becomes very high. The code prints short explanations of two prediction models. The first describes a linear prediction, where plant growth changes at a constant rate as sunlight increases, showing a simple, direct relationship. The second describes a curved prediction that uses sunlight squared, creating a bending pattern. This curved model represents a more complex relationship, where the impact of additional sunlight on growth changes as sunlight levels rise. We begin by setting up a figure and an axis using the subplots function from Matplotlib. This creates the plotting area, or canvas, where we will display and compare different prediction models. We choose a figure size of 6 by 4 inches to keep the visualization clear and easy to interpret. The code uses a scatterplot from the plotting library to show the observed growth data as individual points, with sunlight on the horizontal axis and observed growth on the vertical axis. The points are colored black, so they stand out clearly against the prediction lines. A label is added so these points appear in the legend as observed growth. This visual setup makes it easy to compare the actual data with the predicted models. We use a plotting function from Matplotlib to draw a blue line that shows the linear prediction based on the sunlight values and their predicted outputs. The blue color helps distinguish this prediction line from other elements in the figure. We also assign it the label linear prediction so it appears clearly in the legend. This makes it easier to visually compare the linear prediction with other prediction methods and with the observed data. The code draws a curved prediction line on the graph, using sunlight values along the horizontal axis and the corresponding predicted values on the vertical axis. It colors this line red so it stands out from other lines. The code also adds a label so the curved prediction appears clearly identified in the plot's legend. The code labels the x-axis as sunlight level in arbitrary units, telling us that the horizontal axis shows different amounts of sunlight. It labels the y-axis as plant growth in arbitrary units, so the vertical axis represents how much the plant grows. These axis labels are essential because they explain what the data on the plot means and allow viewers to interpret the relationship between sunlight and plant growth correctly. The code uses the legend feature from the plotting library to add a legend to the graph, which labels each line and set of scatter points. This legend is generated automatically from the labels given when the data is plotted. Including a legend is essential because it lets viewers clearly distinguish between the observed growth, the linear prediction, and the curved prediction, making the plot easier to interpret. We finish by calling the show command from the plotting library, which actually displays the graph we created. This lets us visually compare the observed plant growth with both the linear prediction and the curved prediction. On the plot, the linear model appears as a straight line, while the curved model bends because it includes a squared term. Seeing both lines together makes it easy to notice how the curved prediction differs from the simple linear one. This script compares how linear and curved models make predictions by simulating plant growth under different sunlight levels, with some random noise. The linear model assumes growth increases at a constant rate as sunlight increases, producing a straight prediction line. The curved model adds a squared sunlight term, causing its prediction line to bend. When the simulated data and both prediction lines are plotted together, you can see how the curved model can better match more complex patterns in the observed growth than the simple linear model. balancing flexibility and overfitting, fitting complex patterns. Nonlinear models let us fit complex, curved patterns in data instead of forcing everything into straight lines. Many real processes, such as changes in drug concentration or how learning develops, naturally bend, level off, or have turning points. By using tools like polynomial terms or splines, these models can follow those curves and plateaus more closely. This makes predictions better aligned with how the underlying process actually behaves and avoids misleadingly simple, linear interpretations when the data clearly curves. When modeling relationships like age and income, a simple straight line often fails because income tends to rise early in a career, peak in midlife, and then decline or level off near retirement. To capture this more realistic rise and fall, we use nonlinear features such as squared terms or piecewise curves. This idea also applies in fields like engineering, environmental science, and marketing, where many relationships are not linear. Allowing models to follow the true curved pattern of the data leads to more accurate predictions and better insights. When fitting complex patterns in data, it is important to match the model's complexity to the complexity of the underlying signal. Flexible nonlinear models can reveal key behaviors, such as when extra medication no longer reduces risk or when more advertising stops increasing sales. In medical risk prediction, for example, they can capture a biomarker that is flat at low levels, rises quickly, then levels off. And in climate studies, they can model how energy use changes slowly in mild weather that spikes in extreme temperatures. Overall, nonlinear modeling is powerful for turning raw data into accurate prediction curves while keeping the model appropriately flexible. Python code fitting complex patterns. This script demonstrates how to fit both simple and more complex curves to data, using polynomials as the main example. It highlights the trade-off between having a flexible model that can capture patterns and the risk of overfitting when the model becomes too complex. To make this comparison easy to see, it works with a very small synthetic dataset designed for clear visualization. We begin by importing two key Python libraries, one called NumPy for performing numerical calculations, and another called Matplotlib.pyplot for creating visualizations. These imports provide the main tools we will use to work with data and to draw graphs. With them in place, the rest of the script can focus on analyzing numbers and displaying the results visually. We begin by setting a fixed random seed using the random tools and the numerical library so that any random numbers generated will be identical each time the script runs. This step makes the behavior of the code predictable and repeatable. As a result, other people can run the same script and obtain exactly the same outcomes. This reproducibility is essential when sharing results or verifying experiments. We start by creating a simple input dataset of feature values. Using a numerical tool, we generate 20 evenly spaced numbers between 0 and 10. This range and spacing produce data with a clear curvature, which is useful for showing how polynomial models fit. The choice of 20 points provides enough data to see patterns while keeping the example easy to understand. We model the true relationship between each feature and the target using a quadratic formula. For each feature value, we square it, take half of that result, and then subtract 3 times the original value. This produces a smooth curved pattern that represents the underlying signal in the data before any noise is added. We create random noise using a normal distribution with a mean of 0 and a standard deviation of 5, and we match its size to our x values. This noise represents measurement imperfections by adding random variation to the data. Including this noise makes the simulated data behave more like real-world measurements. We create the observed target values by taking the true underlying curve and adding some random noise to it. This noise represents imperfections in real measurements and makes the data more realistic. The true curve captures the actual relationship we want to learn, while the added noise introduces variability. This variability makes the modeling task more challenging and better reflects real-world data conditions. The function first converts the input array into a NumPy array, so the data is in a consistent format for processing. It then reshapes this data into a column vector, which is necessary for building the polynomial features correctly. This preparation step organizes the input in a structured way and sets it up for creating the polynomial design matrix. We start building our polynomial features by creating a list whose first element is an array of ones. This array acts as the bias term, or intercept, in the polynomial model. Including this bias column lets the model learn the constant term in the polynomial equation. As a result, the model can fit data that does not necessarily pass through the origin. In this loop, we go from 1 up to the chosen polynomial degree, and at each step, raise the input array to the current power. This creates higher-order polynomial terms from the original data. Each new power is then added as a column to the list of features. By the end of the loop, these accumulated columns form the full polynomial design matrix. The code builds a single design matrix by stacking all the feature columns side by side. Each column in this matrix corresponds to a different power of the original input feature. This structure lets the polynomial regression model use these powered features together to fit a more flexible curve to the data. This function returns a design matrix, which is a two-dimensional array containing polynomial features up to a chosen degree. In polynomial regression, this matrix represents the transformed input data used to model the relationship between the inputs and the target variable. By including higher degree terms, the design matrix allows the polynomial model to fit the data more flexibly and capture more complex patterns. The function first builds polynomial features from the input data, turning the original array into a design matrix that includes powers of the input up to a chosen degree. This transformation is necessary for fitting a polynomial model because it lets the model represent nonlinear relationships using higher-order terms. Once this design matrix is created, it is used in the following steps to compute the polynomial regression coefficients. We first convert the target data into a NumPy array and reshape it into a column vector so it matches the dimensions of the design matrix. This alignment is important because it allows matrix operations like multiplication to work correctly during regression fitting. By putting the target values into this column format, we ensure they are ready for the linear algebra calculations needed to solve the normal equations in polynomial regression. This code uses numerical linear algebra to solve the normal equations for polynomial regression. It applies the least squares method to the design matrix and target values to compute the polynomial coefficients. In doing so, it finds the polynomial curve that best fits the data by minimizing the total squared error between observed and predicted values. The resulting coefficients are then flattened into a simple form for convenient use in later calculations. The function outputs the polynomial model's coefficients as a one-dimensional array. This compact format makes the coefficients easier to store and manage. It also simplifies using them in later calculations. In addition, it helps when creating visualizations based on the polynomial model. The function starts by making polynomial model predictions on a new set of input values. It finds the polynomial degree by taking the number of coefficients and subtracting 1, since one coefficient is the constant term. Using this degree, it rebuilds the polynomial design matrix so that the new predictions match the complexity of the original model. We now rebuild the design matrix using the same polynomial degree as before. To do this, we call the function that generates polynomial features, giving it the input data and the chosen degree. This function creates a matrix containing all polynomial terms up to that degree. We will then use this matrix as the basis for making our predictions. This step computes the model's predictions by multiplying the design matrix with the regression coefficients. The design matrix contains the polynomial features of the input data, and the coefficients are the learned weights from the regression model. The coefficients are reshaped so their dimensions match the design matrix for valid multiplication. The result is a set of predicted values for the inputs, which can then be used for plotting or further analysis. The function outputs the predictions as a one-dimensional array by flattening the original two-dimensional prediction data. This flattening step converts the results into a simple, linear format. Doing so makes the predictions easier to work with in later processing. It also simplifies tasks like plotting or analyzing the prediction values. We use two polynomial degrees to compare model complexity. A degree 2 polynomial gives a simple model that captures the main trend without strongly overfitting. A degree 10 polynomial is much more flexible and can fit detailed patterns in the data, but it is more likely to overfit noise. By contrasting these two degrees, we can see how increasing flexibility affects the model's ability to generalize to new data. We generate a smooth grid of input values from 0 to 10 using many evenly spaced points. This grid serves as the basis for drawing prediction curves from our polynomial models. By evaluating the models across this continuous range, we can clearly see how well they fit the data over all possible input values in that interval. We begin by setting up a plotting area using the subplots function from Matplotlib, which creates both a figure and an axis for our graph. This provides the canvas where we will draw the comparison plot. We also specify the figure size as 6 by 4 inches to give a clear, compact view of the data and the fitted curves. We use a scatterplot to show the observed data, placing each point using its x value and its corresponding noisy y value. These points are drawn as black dots, so they are easy to see. We also label them as data points, so the legend clearly identifies what the dots represent. We loop over a list of polynomial degrees, where each degree represents a different level of model complexity. For each degree, we fit a polynomial regression model to the data by calling a function that computes the corresponding polynomial coefficients. These coefficients are calculated from the observed x and y values and describe how the input features relate to the target outcomes for that specific polynomial degree. To evaluate a polynomial model, we compute predictions over a smooth range of x values. We use a polynomial prediction function that takes this grid of x values and the fitted coefficients as inputs. The function calculates the corresponding y values at each point on the grid. These predicted values then let us see how well the polynomial model fits the data across the full range of x. The code chooses a line style based on how complex the polynomial model is. When the polynomial has degree 2, it uses a solid line to show this simpler model. For higher degree models, such as degree 10, it switches to a dashed line. This visual difference makes it easy to tell simpler and more complex fits apart in the plot. We use the plotting function from Matplotlib to draw the model's curve by feeding it the x values from our grid and the corresponding predicted y values from the polynomial. The line style reflects model complexity, with a solid line for simpler polynomials and a dashed line for more complex ones. We also add a label that states the polynomial degree, so different model curves can be easily distinguished in the plot. This code sets the label for the horizontal axis of a plot indicating that it represents the input quantity, called the feature x. By naming the axis, it clarifies what the values along the x-axis mean in the context of the data. This helps viewers quickly understand how to interpret the plotted information. The code sets the label for the vertical axis of the plot to indicate that it shows the model's predicted outcome. This tells the viewer that the values along this axis come from the polynomial regression models. By labeling the axis this way, it becomes clear that the plot is comparing predicted results from different models, rather than showing raw or observed data. The plot title is chosen to highlight the comparison between simple and complex polynomial fits. It draws attention to the trade-off between flexibility and overfitting, which is key to understanding how the degree of a polynomial affects model performance. By stating this contrast clearly, the title helps viewers quickly grasp that the plot is about how well different polynomial models generalize from data. The code uses the legend feature from the plotting library to add a legend to the graph. This legend labels each model curve by its polynomial degree. As a result, you can easily see which curve corresponds to which degree. This makes the plot clearer, more informative, and easier to interpret. This message explains that a polynomial model of degree 2 captures the main trend in the data, while ignoring much of the random noise. By not trying to match every small fluctuation in the observations, the model stays simpler and more stable. This illustrates how a less complex model can avoid overfitting and still represent the underlying pattern effectively. This explanation describes how a 10th degree polynomial model behaves. Because it is so flexible, the model bends sharply to match the training data. This extreme bending shows overfitting, where the model learns noise instead of the true underlying pattern. As a result, it does not generalize well and performs poorly on new data. The code uses a plotting library to display the graph that has been built, showing the observed data along with polynomial fits of different degrees. When the display function is called, a window opens so you can see the data points and the fitted curves together. This visual comparison is important for judging how well each polynomial model matches the data, and for noticing the differences between simpler and more complex models. This script shows how fitting polynomial curves to data illustrates the trade-off between model simplicity and overfitting. It creates noisy data that follow a quadratic relationship, then fits both a quadratic model and a much more flexible 10th degree model. The quadratic model captures the main trend without reacting too strongly to the noise, while the 10th degree model bends sharply to match the noise and therefore overfits. By comparing these two fitted curves, the example makes clear how increasing model flexibility can increase the risk of overfitting to random fluctuations in the data. Overfitting dangers. When a nonlinear model becomes too flexible, it can closely follow many individual data points, but start to overfit. Instead of learning general patterns, it may memorize random quirks in the training data. This makes it look very accurate on the training set while performing poorly on new data. In this case, the model is confusing noise for meaningful signal, so its apparent accuracy during training is misleading. When a nonlinear model for predicting house prices is too flexible, it can mistake short-term fluctuations, like a temporary drop during an economic downturn, for a lasting pattern. This leads the model to produce sharp dips in its predictions that look accurate on the training data, but fail when the market changes or when used on new houses. In this situation, the model has learned noise instead of the true relationship between features such as size and neighborhood and the actual prices. This problem, known as overfitting, causes biased predictions and higher errors on new data. Overfitting in nonlinear models is dangerous because the model can closely follow random noise while still appearing highly accurate. In sensitive areas like medicine or finance, this means the model may learn patterns that only exist in one dataset, such as quirks from a particular hospital or a specific period in the market. As a result, its predictions can fail badly when used in new hospitals or under different market conditions. The main risk is that these models create false confidence, looking reliable during development, but breaking down on new data and leading to serious, costly mistakes. Python code overfitting dangers. This script visually demonstrates how nonlinear models can overfit data. It compares simple curves with more complex wiggly curves when the data contain noise. The key idea is to see how models that fit the training data very closely can perform poorly on new, unseen data. Throughout, the focus is on understanding the difference between training error and testing error when evaluating prediction performance. The script explains that all required libraries are already available in the Colab environment, so you do not need to install them there. If you run the code in a different environment, you may need to install these libraries yourself. It includes a commented example of how to install a library such as Matplotlib using a package manager, but this is disabled because it is unnecessary in Colab. This setup keeps the focus on demonstrating the dangers of overfitting without extra installation steps. We begin by importing two key libraries for our work. NumPy is used for efficient numerical computations, especially for working with arrays and performing mathematical operations. Matplotlib's plotting tools let us create visualizations of our data. Together, these libraries allow us to generate data and plot it, so we can study how overfitting occurs in machine learning models. We set a fixed random seed using the numerical library's seed function with the value 42 to make our results reproducible. This means that every time the script runs, it will generate the same sequence of random numbers. Having consistent random output is important because it allows us to reliably repeat experiments, debug issues, and verify that the code behaves as expected. We begin by generating our training inputs using a numerical tool that creates 20 evenly spaced values between -3 and 3. These values act as our one-dimensional input features, giving us a set of x values on which to base our model. This simple setup mimics a real situation where we only have a limited number of observations available for training. We generate the true signal for our training data by applying the sine function to the input values. This produces a smooth, nonlinear pattern that represents the underlying relationship we want the model to learn. Because the sine function is periodic and predictable, it gives us a clear reference pattern. We will later compare this true signal to noisy observations to evaluate how well the model captures the underlying trend. We add random noise to the training data to make it more realistic and challenging for the model. This noise is generated from a normal distribution with a mean of 0 and a standard deviation of about 0.3. The noise array is created so that it has the same shape as the training inputs. By doing this, we simulate the natural variability found in real-world data, helping the model learn to handle imperfect and noisy inputs. We create the observed training targets by adding random noise to the true underlying signal. This mimics real-world data, where measurements are rarely perfect and often include random fluctuations. By combining the signal and the noise, we obtain a more realistic dataset for training the model. This allows us to test how well the model can learn the true pattern, even when the data are noisy. We generate a set of test inputs using a numerical tool that creates 100 evenly spaced values between -3 and 3. This range matches the training data, so it lets us check how well the models generalize to new points in the same region. Using many closely spaced values also helps us see the model's behavior smoothly across the entire input space. To obtain the true signal for our test inputs, we apply the sign function to each value in the test set. This produces a smooth, noise-free pattern that represents the ideal output. We then use this clean reference signal to judge how well our models generalize to new, unseen data. This function prepares data for building polynomial features by first converting the input into a one-dimensional array. It does this by turning the input into a NumPy array and reshaping it into a flat structure. Ensuring a consistent one-dimensional format is essential so that later steps that construct the polynomial features can process the data reliably. The code starts by creating a list of features that begins with an array of ones matching the shape of the input data. This array of ones represents the zero power of the input and acts as the constant term in polynomial regression. It serves as the base of the design matrix, which will later be expanded with higher powers of the input values. This setup is essential for constructing the polynomial features used when fitting models to the data. In this part of the code, a loop runs from 1 up to the chosen polynomial degree, and in each step it raises the input values to the current power. The results of each power calculation are added to a growing list of features. By the end of the loop, this list contains polynomial features, meaning the original inputs raised to increasing powers. These features are then used to form the design matrix needed for polynomial regression. The code builds a matrix by taking powers of the input values as features and stacking them together. It then transposes this matrix so that each feature becomes a separate column. This structure is required for polynomial regression because it matches the format needed for linear algebra operations used when fitting the model. We use a helper function to fit a polynomial to data using the least squares method. It first builds a matrix of polynomial features from the input values, up to a chosen degree. This feature matrix then serves as the basis for fitting the polynomial model to the data. In this way, the function prepares the data and performs the fitting in one streamlined step. Before solving the linear system, the code first checks that the number of rows in the polynomial feature matrix matches the number of target values. This confirms that every input has a corresponding output. Having this one-to-one match is essential for the least squares fitting process to be valid and work correctly. We use a least squares function from a numerical library to solve the normal equations for our polynomial model. This function takes the matrix of polynomial features and the target values, then finds the coefficients that make the predicted values as close as possible to the actual values in terms of squared error. Its output includes a vector of optimal coefficients, which we extract and use as the parameters of the polynomial model. This function returns the polynomial coefficients learned from fitting the model to the data. These coefficients act as weights for each term in the polynomial equation. With them, we can make predictions from the input features. In other words, the returned vector contains all the parameters needed to describe the fitted polynomial curve. This function generates predictions based on a set of polynomial coefficients. It first finds the degree of the polynomial by taking the length of the coefficient list and subtracting 1, since the list includes the constant term. Knowing the degree is essential because it tells the function how many powers of the input to include. With this information, it can build the correct feature matrix and then use it to produce the predicted values. To build the feature matrix for new inputs, we use a helper function that generates polynomial features from the data and the chosen polynomial degree. It creates a matrix where each column is the input values raised to a different power, starting from 0 up to the specified degree. This structure is crucial because it matches the format used when training the polynomial model. As a result, it allows us to correctly combine the input data with the learned coefficients to make predictions. The code makes predictions by multiplying the feature matrix with the model's coefficients. This matrix multiplication applies the polynomial model to the input data. As a result, it produces predicted values that reflect the learned relationship captured in those coefficients. We fit a simple polynomial model of degree 2 to our training data. To do this, we use a fitting function that takes the training inputs, the noisy training targets, and the chosen polynomial degree. The function applies the least squares method to find the polynomial coefficients that best match the data. These coefficients are then stored for later use when we want to make predictions with this simple model. We fit a very flexible polynomial model to our training data by using a 12th degree polynomial, which allows the model to include powers of the input variable up to 12. This produces a set of coefficients that define a complex curve closely matching the training inputs and targets. Such a high-degree model can capture intricate patterns in the data, but it also increases the risk of overfitting, where the model learns noise instead of true underlying structure. We now use the simple polynomial model to make predictions on the training data. To do this, we take the original training inputs, build the corresponding polynomial features, and then multiply this feature matrix by the previously learned coefficients. This calculation produces predicted output values for each training example. By comparing these predictions to the actual training outputs, we can evaluate how well the simple polynomial model fits the training set. We now use the complex polynomial model to make predictions on the training data. Using the previously estimated coefficients, the prediction function builds the appropriate polynomial features from the training inputs and multiplies them by these coefficients to produce predicted values. This step lets us see how well the complex model fits the training data, which is important for later comparing its performance to the simpler model. We now use the simple polynomial model to make predictions on the test data. To do this, we take the test input values, build the corresponding polynomial features, and apply the learned coefficients from the model. This process produces predicted outputs for each test example. We can then use these predictions to assess how well the simple model generalizes beyond the training data. We now use the complex polynomial model to make predictions on the test inputs. Using the coefficients learned during training, the prediction function builds the required polynomial features from the test data and applies matrix multiplication to compute the predictive values. This process lets us see how well the complex model performs on unseen data and helps reveal whether it may be overfitting to the training set. This function computes the mean squared error between two arrays, a standard way to measure how accurate predictions are. It first reshapes the array of true values into a one-dimensional form. This reshaping step ensures the true and predicted values have compatible shapes. With aligned shapes, the function can correctly calculate the average of the squared differences between them. The code reshapes the predictions into a one-dimensional array, so they all share a consistent format. This flat structure is important because many later steps, such as calculating errors or making comparisons, expect the predictions to be in this simple form. By standardizing the shape in this way, the predictions are easier to process, analyze, and plot. We make sure that true values and the predicted values have the same length, so we can compare them correctly. When their lengths match, we can safely perform element-wise operations, such as subtracting one from the other. These operations are essential for computing errors or differences between the two arrays. Without matching lengths, these calculations would not be valid or reliable. This line computes the mean squared error, a standard measure of how far predicted values are from the true values. It first reshapes both sets of values into one-dimensional arrays and checks that they have the same length. Then it calculates the squared difference for each pair of true and predicted values and takes the average. The result is a single number that represents the overall magnitude of the prediction error. To measure how well the simple model fits the training data, we use the mean squared error. This measure compares the true training values with the model's predicted values. It does this by taking the differences between them, squaring those differences, and then averaging the result. The final value tells us how large the typical squared error is for the model on the training data. To evaluate the complex model on its training data, we use the mean squared error. This measure compares the true training values with the model's predictions and computes the average of the squared differences between them. The resulting value tells us how well the complex model fits the data it was trained on and summarizes its training performance. To evaluate the simple model on new data, we use the mean squared error. This measure compares the true test values with the model's predicted values. It calculates the average of the squared differences between them. A smaller mean squared error indicates that the model generalizes better to unseen data. To evaluate the complex model, we compute its test error using the mean squared error. This measure compares the true test values with the model's predicted values by averaging the squared differences between them. A lower mean squared error indicates that the model's predictions are closer to the actual test data. By examining this error on unseen data, we can assess the model's performance and detect possible overfitting. We report the mean squared error of the simple model on the training data to measure how well it fits the training set. This value represents the average of the squared differences between the model's predictions and the actual target values. It provides a single, concise number that summarizes the model's performance. We round this value to 3 decimal places to make it easier to read and to compare with the performance of other models. We report the mean squared error of the complex model on the training data, rounded to 3 decimal places. This value illustrates that the complex model seems to perform better on the training set because its higher flexibility allows it to fit the training data more closely. The key idea is that greater model complexity can reduce training error, at least on the data it was trained on. We report the mean squared error of the simple model on the test data to measure how well it generalizes to unseen examples. This error value indicates how accurately the model predicts new data, beyond what it learned during training. We round the error to 3 decimal places, so the result is concise and easy to interpret. This step helps us quickly assess the model's overall predictive performance. We report the mean squared error of the complex model on the test data, rounded to 3 decimal places, to show how it actually performs on new examples. Even though this model fits the training data very well, its high error on the test set reveals that it is overfitting. This poor performance on unseen data demonstrates that the model does not generalize well beyond the training set. We begin by setting up a plotting area using a figure and axis created with a subplots function. This gives us a clear canvas where we can display both the data and the model curves. The figure size is chosen to make the comparison easy to see. This visual setup is important because it lets us clearly compare simple and complex models and illustrate how overfitting appears in practice. The code uses a scatter plot from a plotting library to show the training data as individual points. It takes the input values and their corresponding noisy target values and displays them as black dots so they stand out clearly. The points are labeled as training data so they can be identified in the legend. This visual makes it easier to compare the actual data points with the model's predictions and the true underlying pattern. The code uses a plotting library to draw the true smooth sign relationship as a green line based on the test input values and their exact sign outputs. This line represents the real pattern in the data that the models are trying to learn. By comparing the model predictions to this reference line, we can visually judge how well each model fits the true underlying relationship. We now plot the simple model's predictions on the test data. The x values from the test set are fed into the model, and the resulting predicted y values are drawn as a continuous line. This line is colored blue, so it stands out visually, and it is labeled as simple model, so it can be clearly identified in the plot's legend. This step plots the complex model's predictions on the test data, using the test inputs and the model's outputs. Because the model is overfitting, its prediction curve appears wiggly rather than smooth. The line is drawn in red and labeled as the complex model, so it can be easily distinguished from other curves in the plot. The plot title is chosen to emphasize the idea of overfitting. It shows how a very complex curve can match the random noise in the training data instead of the true pattern. As a result, the model performs poorly on new unseen test data. This visual focus helps explain that when a model is too closely tailored to the training data, it loses its ability to generalize. The code sets the label of the horizontal axis to indicate that it shows the input feature x values. This label clarifies what the x-axis represents in the plot. As a result, viewers can easily understand that the horizontal axis corresponds to the input features used in the model. The code sets the label for the vertical axis of the plot to indicate what it represents, in this case the predicted y value or true signal. This label explains the meaning of the values shown along that axis. By clearly naming the axis, it helps viewers understand what the model is predicting or what the true output is. As a result, the relationship between the input features and the predicted or true output values becomes easier to interpret. The code adds a legend to the plot so we can clearly tell the different curves and data points apart. By calling the legend function on the axis, the legend is placed automatically in a good location for readability. This makes it clear which line represents the training data, the true pattern, the simple model, and the complex model. As a result, it becomes easier to understand what the plot is saying about overfitting. We then display the plot to visualize how the two models behave. The figure compares the simple model and the complex model on both the noisy training data and the test data, along with the true sine wave. It clearly shows that the complex model closely follows the noise in the training data, but fails to generalize to the test data. This provides a visual demonstration of how overfitting can lead to poor performance on new data. This script illustrates overfitting by comparing two polynomial models trained on noisy data generated from a sine wave. A simple quadratic model captures the overall trend, while a much more complex 12th degree polynomial bends to match the noise. On the training data, the complex model appears better because it achieves lower error. However, when tested on new data, the simple model keeps reasonable accuracy, and the complex model performs poorly. The resulting curves show a smooth, stable shape for the simple model and a highly wiggly overfit shape for the complex one, revealing that low training error does not guarantee good generalization. Model validation essentials. For nonlinear models, validation is essential to avoid overfitting and to check how well the model works on new data, not just the training set. We do this by holding back part of the data during training and later using it to test the model's accuracy. By comparing performance on the training data and the validation data, we can see whether the model has truly learned the underlying pattern or is just fitting noise. This separation is especially important for nonlinear models, which can more easily memorize noise than simpler linear models. In nonlinear modeling, a common strategy is to try models with different levels of flexibility and choose the one that works best on unseen data. More flexible models can fit training data very closely, but this does not guarantee good performance on validation data. As flexibility increases, validation performance usually improves at first, then worsens when the model starts fitting noise instead of true patterns. This behavior illustrates the need to balance capturing real structure in the data with avoiding overfitting, so you select a model that is complex enough to be accurate. In real-world settings like healthcare and finance, strong validation is essential, especially when data is limited or noisy. Splitting data into different training and validation sets, or using time-ordered validation, helps check that a model's performance is not just a lucky result. If a model does well on one split, but poorly on another, it may be too tailored to specific cases and not generalize well. By testing across multiple scenarios and treating validation as an ongoing process, you can better balance model flexibility with the risk of overfitting. Python code. Model Validation Essentials. This script introduces basic ideas of model validation by comparing flexible and simple polynomial curve fits. It highlights how more complex models can overfit the data, while simpler models may generalize better to new data. The main focus is on understanding the trade-off between overfitting and generalization using validation techniques. The commented line with the exclamation mark represents a command to install several Python libraries using pip. These libraries are NumPy for numerical work, Pandas for data handling, Matplotlib for plotting, and Seaborn for statistical visualization. Such a command is often used in environments like Jupyter Notebooks to make sure all required packages are available. Because the line is commented out, it suggests that the installation has likely already been done or is optional in the current setup. We begin the script by importing two key libraries. We use NumPy to handle numerical calculations and data manipulation, which supports all the core computations in the code. We also import the plotting tools from Matplotlib to create visualizations and graphs. Together, these libraries provide the foundation for both the numerical work and the visual analysis that follow in the script. We set a fixed random seed using the random number generator in NumPy with a seed value of 42. This makes the sequence of random numbers the same every time the code runs. As a result, the model's behavior can be reproduced consistently. This reproducibility is important for debugging, testing, and validating the results. We create a one-dimensional set of input values using a function that generates evenly spaced numbers. It produces 60 points ranging from -3 to +3. This choice of range and number of points gives us a smooth, continuous set of inputs. These inputs are then suitable for use in modeling and analysis tasks. We begin by defining the true target values using a smooth cubic function, where each output is given by 1/2 times x cubed minus x. Here, x represents the input values, and this formula produces a smooth curve that we treat as the real underlying relationship between x and y. Establishing this true curve is important because it provides a baseline that we will later compare with noisy data to see how well our models can recover the original pattern. We use a random number generator to add noise to our data, so it better reflects real-world observations. This noise comes from a normal distribution with a mean of 0 and a standard deviation of 3. We create the noise array to match the shape of the input data, so each value gets its own noise term. Adding this variability lets us test how well the model performs when the data are imperfect. We start with true target values generated from a smooth cubic function and then add random noise to them. This step is important because it makes the data resemble real-world observations rather than a perfect mathematical curve. The added noise introduces variability while still preserving the underlying trend of the cubic function. As a result, Our target values capture both the smooth pattern and the randomness found in actual data. We begin by creating an index array that matches the length of our input data. This array assigns a unique index to each data point, so every element in the dataset can be clearly identified. Using a numerical range function, we generate indices from 0 up to the total number of data points. These indices then make it easy to manage the dataset and split it into training and validation subsets. The code uses a random number generator with a fixed seed to shuffle the array of indices in a deterministic way. This shuffling randomly mixes the data, while still being repeatable. By doing this, the training and validation datasets are formed without order-based bias. As a result, the model's performance can be evaluated more fairly and accurately. The code sets the training dataset size by taking the total number of input values and dividing it by 2. So the data is split into equal training and validation parts. This means half the data is used to train the model, and the other half is used to check how well it performs on data it has not seen during training. This split is important because it helps evaluate how well the model generalizes beyond the data it was trained on. We build a Boolean mask to mark which data points belong to the training set. To do this, we take the first half of the shuffled indices, which represent the training portion of the data. This mask then lets us pull out the corresponding inputs and target values from the full dataset. In short, the mask is a tool for separating training data from the rest of the data. We create the validation indices by taking the remaining elements from the shuffled list of data indices, starting right after those used for training. This process splits the dataset into 2 distinct parts, one subset for training the model and the other for validation. Using this separate validation set lets us test how well the model performs on data it has not seen during training. We create the training inputs and targets by using the indices we previously selected for the training set. Using these indices, we pick out the corresponding elements from the full input array and the full target array. This gives us smaller subsets of the original data. These subsets are what we use to fit our models, so the training process is based only on this specific portion of the data. We create the validation inputs and targets by selecting the data points whose indices were assigned to the validation set. This means we take only those input values and their corresponding target values that match the validation indices from the full dataset. Doing this allows us to test the model on data it has not seen during training. As a result, we can more accurately measure how well the model is likely to generalize to new, unseen data. Before training a model, we must check that the shapes of the input data and the target values match. Each input example needs a corresponding target, so any mismatch will cause errors when fitting the model. By confirming that these shapes are consistent, we help ensure the training process runs smoothly and avoid problems during model fitting. We use an assertion here to make sure the validation input and target arrays have matching shapes. This check confirms that every input value has a corresponding target value, which is essential for evaluating the model correctly. By enforcing this condition, we can detect mismatched data early and avoid errors during the validation process. We choose polynomial degrees of 1, 3, and 9 to create models with different levels of flexibility. These degrees let us fit simple, moderate, and more complex polynomial models to the same data. By comparing how these models perform on both training and validation data, we can see how increasing complexity affects generalization. This helps illustrate the trade-off between underfitting with models that are too simple and overfitting with models that are too complex. We begin by creating 2 empty lists to record how our polynomial models perform. One list will store the mean squared error values on the training data, and the other will store the mean squared error values on the validation data. By filling these lists as we change the complexity of the polynomial models, we can track and compare their performance on both datasets. We run a loop over a list of polynomial degrees so we can fit models of different complexity to the training data. By comparing how each degree performs on both the training and validation sets, we see how increasing flexibility changes the results. This process helps us understand the balance between models that are too simple and underfit the data, and models that are too complex and overfit it. In other words, it is a way to study how model complexity affects validation performance. We use a polynomial fitting function from NumPy to model the relationship in the training data. This function performs a least squares fit, meaning it chooses polynomial coefficients that minimize the squared difference between predicted and actual target values. The degree of the polynomial controls how flexible the model is. By adjusting this degree, we can study how different levels of model complexity affect the ability to generalize from the training data. We use the fitted coefficients to build a polynomial function that can quickly generate predictions for any input value. By packaging the coefficients into this single function, we can easily apply the same model to both the training and validation data. This makes it straightforward to compare how well models of different polynomial degrees perform on each dataset. We use the polynomial model built from the fitted coefficients to generate predictions for both the training and validation data. First, we apply the polynomial to the training inputs to obtain predicted training values. Then, we apply the same model to the validation inputs to get predicted validation values. Comparing these predictions helps us judge how well the polynomial model generalizes to new, unseen data. To compute the mean squared error on the training data, we first find the difference between each predicted value and its actual target value. We then square these differences to give more weight to larger errors. Next, we take the average of all the squared differences using a numerical mean function. Finally, we convert this average to a standard floating point number so it is ready for further analysis. To compute the mean squared error on the validation set, we first find the difference between each predicted value and its actual target value. We then square these differences so that larger errors have a greater impact. Next, we take the average of all the squared differences using a numerical mean function. Finally, we convert this average to a standard floating point number so it can be used consistently in later analysis. We record the training mean squared error in a list, so we can track how it changes as we increase the polynomial degree. This record shows how the model's performance on the training data evolves with model complexity. By examining these stored errors, we can better understand and analyze the trade-off between using a more complex model and the risk of overfitting the training data. The code records the validation mean squared error in a list for each polynomial degree. This list collects the error values as the model becomes more or less flexible. By comparing these stored errors later, we can see how changing the polynomial degree affects the model's performance on new, unseen data. The code prints a brief summary of how the model performs by showing the polynomial degree together with the mean squared error for both the training and validation data. This lets you quickly see how well each version of the model fits the data. It also helps you compare different model complexities and understand the trade-off between fitting the training data closely and generalizing well to new data. We examine each polynomial degree along with its training and validation mean squared error to see how performance changes as model complexity increases. By looping through these values, we can compare how different polynomial models fit the data and how well they generalize. This process helps us understand the trade-off between having a more flexible model that can capture complex patterns and the risk of overfitting, which harms performance on new data. We display a formatted message that reports the polynomial degree along with the training and validation mean squared errors. This lets us see how both errors change as we increase the model's flexibility by using higher degree polynomials. The degree is listed first, followed by the training error, and then the validation error. Each error value is rounded to 2 decimal places to keep the output clear and easy to interpret. We generate a dense grid of input values from -3 to 3, using 200 evenly spaced points. This grid serves as the basis for plotting the model's fitted prediction curve. By evaluating the model at each point in this continuous range, we can clearly see how its predictions change across different input values. We begin by creating a figure and an axis using a plotting library such as Matplotlib. The figure, set to a size of 6 by 4 inches, acts as the main canvas for our visualizations. The axis provides a space where we can draw plots, add labels, and include other elements. Together, they prepare the layout needed to display both the data and the model curves clearly. We use a scatterplot from a plotting library to show the training data on a graph. The input values are placed along the horizontal axis and the output values along the vertical axis. Each training example appears as a blue dot, giving a visual picture of the dataset. We also assign a label called trained data, so these points can be clearly identified in the legend and distinguished from other elements in the plot. This line uses a plotting library to show the validation data as orange scatter points on the graph. It takes the x and y values of the validation set and plots them with a label called validation data. This label appears in the legend, so listeners can distinguish these points from other data and model curves. Overall, it makes the validation data visually and clearly separate from the rest of the plot. We first plot the true underlying cubic function as a reference curve. To do this, we evaluate the function, which is 1/2 of x cubed minus x, on a dense set of x values, and use a plotting tool to draw the resulting smooth curve. The curve is shown in black for clear visibility and labeled as the true curve, so it can be easily distinguished from any other data or model predictions that may be plotted alongside it. We are plotting fitted curves for several polynomial degrees and want each one to have a different color. To do this, we take our list of degrees and pair each degree with a color from a predefined list, such as green, red, and purple. We use a function that lets us loop over both lists at the same time, assigning one color to each degree. This way, every polynomial curve appears in a distinct color, making it easy to tell the different polynomial fits apart on the graph. We refit the polynomial to the training data so we can plot how well it models the data. Using a numerical fitting function, we compute the polynomial coefficients for a chosen degree. These coefficients define the curve that best matches the training data in the least squares sense. This refitting step is essential for comparing how different polynomial degrees capture the underlying pattern in the data. The code evaluates the polynomial on a dense set of x values to produce a smooth curve. It uses a numerical tool that takes the polynomial's coefficients and these x values as inputs, and returns the corresponding y values. These y values trace out the polynomial curve, making it possible to visually compare how well models with different polynomial degrees fit the data. This code adds a polynomial curve to an existing plot using the current degree of the polynomial model. It creates a smooth set of x values on a dense grid and computes the corresponding y values from the polynomial predictions. The curve is drawn with a dashed line and colored according to the current iteration. The label includes the polynomial degree, so different models can be easily distinguished on the plot. The code sets the horizontal axis label of the plot to say input feature x. This tells the viewer that the x-axis shows the input values used in the model. Adding this label makes the plot easier to interpret and connects the axis directly to the model's input feature. The code labels the vertical axis of the plot as target y. This tells the viewer that the values along this axis correspond to the target variable in the dataset. By naming the axis clearly, it provides context for understanding the plotted data and any model predictions shown in the graph. Adding a legend to the plot makes it easier to tell different datasets and model curves apart. When you call the legend function on the axis, it automatically chooses a good position, so the labels do not cover important parts of the plot. This improves clarity and readability, which is essential for correctly interpreting the data. It also helps you compare how different polynomial models perform in a clear and organized way. We then use the plotting library's show function to display the final figure. This figure includes the training and validation data points, the true underlying function, and the fitted polynomial curves. By viewing them together, we can visually compare how well each polynomial degree matches the data. This makes it easier to judge model performance and see the trade-off between using a more complex model and achieving good generalization. This script shows how model validation works by fitting polynomial curves of different degrees to noisy data. It generates data from a cubic function with added noise, then splits it into training and validation sets. Polynomials of degree 1, 3, and 9 are fitted, and the mean squared error is computed on both sets to reveal how increasing model complexity can lead to overfitting. The printed errors and a final plot comparing the data, the true function, and the fitted curves illustrate how well each model generalizes beyond the training data. In this lecture, you learned to recognize visual patterns in data that suggest nonlinear relationships, describe how adding transformed features can create curved prediction shapes, and explain the trade-off between flexibility and overfitting in nonlinear models. In the next lecture, Lecture B, we will go over piecewise decisions.
Thank you for your attention. See you all in the next lecture.